this is John Whitaker again for the Mathematical Analysis 2 class, and this is our 28th video lecture. We're still talking about uniform convergence for a sequence of functions and what that preserves, what types of limit processes that preserves. And I want to start off today with a theorem. And here we have alpha being a monotonically increasing function on A to B, and suppose f sub n's are Riemann-Stieltjes integral with respect to alpha on A to B. And that's for n equaling 1, 2, 3, forever. And suppose that the sequence of f sub n's converge uniformly to f on A to B, then f is Riemann-Stieltjes integral with respect to alpha on A to B, and turns out that the integral from A to B of f d alpha is equal to the limit as n goes to infinity of the integral from A to B of the f sub n's d alpha. So uniform convergence allows us to pull the limit outside the integral, because this is the limit as n goes to infinity of the f sub n's. That's what this is. So we're pulling the limit outside. That's wonderful. So uniform convergence helps us move that limit. This function is really, when we talked about Riemann-Stieltjes integral functions, we always talked about real value functions. But it turns out that we could really extend that to complex value functions. And we did have an extension to complex value functions, if you will, with vector value functions, and that's the way we think of complex value functions. But here, we know that that extension can occur where we can just consider the f sub n's to be real value functions. So that's what we're going to look at. So our proof, okay, so in our proof, I'll say it's enough to consider only real value functions f sub n. All right. So we will let alpha be monotonically increasing f sub n's, the elements of the Riemann-Stieltjes integral functions with respect to alpha on A to B. And this is true for n equaling 1, 2, 3, and forever. And suppose that the sequence of the f sub n's converge uniformly to this function f on the integral from a to b. Okay. We want to show f, the limit function, is Riemann-Stieltjes integral with respect to alpha on a to b, and that the integral from a to b of f d alpha is really equal to the limit as n goes to infinity of the integral a to b of f d alpha, f sub n d alpha. Okay. Now, one of the things in terms of the f sub n to be a Riemann-Stieltjes integral is that we're assuming excuse me, that the f sub n's are bounded functions. Sorry. Okay. By having f sub n be Riemann-Stieltjes integrable with respect to alpha. Okay. So, since the f sub n's converge uniformly to f, then what we have is that f is going to be a bounded function. Okay. Okay. Thus, for each natural number, n, what we do is we let epsilon sub n be equal to the supremum over a to b of f sub n of x minus f of x. Then for each n, okay, we have that the norm of f of n of x minus f of x is going to be less than or equal to epsilon sub n, and that's true for all x element of a d. So, for each n, and for all x element of a to b, we have, okay, this says that minus epsilon over n be less than or equal to f sub n of x minus f of x, which is less than or equal to epsilon over n. And that implies that minus f of n of x minus epsilon sub n be less than or equal to minus f of x, which is less than or equal to epsilon sub n minus f of n of x, which implies that f of n of x minus epsilon sub n will be less than or equal to f of x, which will be less than or equal to f of n of x plus epsilon over n. Okay. Thus, we have the lower Riemann-Stieltjes integral of f sub n of x minus epsilon sub n d alpha is less than or equal to the lower Riemann-Stieltjes integral of f, which is going to be less than or equal to the upper Riemann-Stieltjes integral of f, which is going to be less than or equal to a to b, the upper one, or upper interval from a to b, of f sub n of x plus epsilon sub n d alpha. Thus, okay, look, this s sub n of x minus epsilon sub n, that's a Riemann-Stieltjes integral function. And so we have just the overall integral. D alpha will be less than or equal to the lower integral of f, which is less than or equal to the upper integral of f, which is less than or equal to, here again we substitute this with just the Riemann-Stieltjes integral. Because they are the same in that f sub n plus epsilon sub n is Riemann-Stieltjes integral. Okay. So, the difference between these two guys, the upper and lower intervals, will be less than the difference between these two intervals. So we have that this difference between the upper and the lower integrals of f is less than or equal to, well, we can combine these two functions with one integral, and f sub n minus f sub n, that cancels each other. And so we're left with the integral from a to b of 2 epsilon sub n d alphas. But this is a constant. And so what we get is that the difference between the upper and the lower integrals is going to be less than or equal to, so I'll pull out this constant and then just integrate one, or integrate just the constant we know is alpha of b minus alpha of a. Okay, since the f sub n's converge uniformly, to f on a to b, then the epsilon sub n's go to the limit that then goes to infinity of epsilon sub n equals to 0. And this is true by a previous theorem. And so, since the epsilon sub n's go towards 0, then the difference between the upper and lower sum is arbitrarily small, and we can say that the upper sum, I'm sorry, not upper sum, but the upper interval. So what I should have said is that the difference between the upper interval and lower interval is arbitrarily small. So that means that these are equal to each other. Okay. And thus, F is Riemann-Stieltjes integral on A to B. We now want to show that the integral from A to B of f d alpha equals to the limit as n goes to infinity of the integral from A to B of f sub n d alpha. Okay, we'll start off by letting epsilon be greater than 0 be given. We need, this is a limit problem, we need a natural number n such that for all n greater than or equal to this big N, the absolute value of the integral from A to B of f sub n d alpha minus the integral from A to B of f d alpha will be less than epsilon. Okay? Now, since the integral from A to B of f sub n minus epsilon sub n d alpha is less than or equal to the integral from A to B of f d alpha, which is less than or equal to the integral from A to B of f sub n plus epsilon sub n d alpha, that's by our previous work essentially, then the integral from A to B of f sub n d alpha minus the integral from A to B of epsilon sub n d alpha is less than or equal to the integral from A to B of f d alpha, which is less than or equal to the integral from A to B of f n d alpha plus the integral from A to B of epsilon sub n d alpha. Just splitting up the integrals here. And so this says, if we subtract the integral from A to B of f sub n d alpha, we have that minus epsilon sub n times alpha of b minus alpha of a. That's what this part is. It'll be less than or equal to the integral from A to B of f d alpha minus the integral from a to b of f sub n d alpha, which will be less than or equal to this integral, which we know to be epsilon sub n times alpha of b minus alpha of a. And so that means that the absolute value of the integral from a to b of the f sub n's is the way I'll write it, d alpha. So that's the value of this, and I'll write the f sub n's first. Minus the integral from a to b of f d alpha is less than epsilon sub n times alpha of b minus alpha of a. And since the limit as n goes to infinity of epsilon sub n equals to 0, then there exists a natural number n such that for all n bigger than or equal to big N, epsilon sub n will be less than epsilon over the quantity alpha of b minus alpha of a. Okay, so for all n bigger than or equal to big N, this absolute value of the integral from a to b of f sub n d alpha minus the integral from a to b of f d alpha will be less than epsilon. Thus, we have the result we wanted, in that the limit as n goes to infinity of the integral from a to b of f sub n d alpha is equal to the integral from a to b of f d alpha. Wonderful. As a corollary to that, if f sub n are Riemann-Stieltjes integral functions with respect to alpha on a to b, and if f of x is equal to the sum as n runs from 1 to infinity of f sub n of x, where x is an element of a to b, with the series converging uniformly, then uniformly on a to b, then the integral from a to b of f d alpha is equal to the sum as n runs from 1 to infinity of the integral of a to b of f sub n d alpha. So we can integrate term by term here. let's look at proof. Our text doesn't list the proof here, but I will. We're going to let f sub n's be Riemann-Stieltjes integral functions with respect to alpha on a to b, and let f of x equal to the sum as n runs from 1 to infinity of f sub n of x, where x is an element from a to b. To get a better, more detailed description of the convergence of this sum being uniformly, I'll say consider f sub k, that's a k, of x being equal to the sum as n runs from 1 to k of f sub n of x. Okay? And let the f sub k of x, or f sub k, I should say, as k runs from 1 to infinity, converge uniformly to f on a to b. Okay, so here's an observation. That is that the f sub k's of x equaling to the sum as n runs from 1 to k of f sub n of x. Okay. That is an element. So the f sub k's are elements of Riemann-Stieltjes integral functions with respect to alpha on a to b. And that's true because each one of the f sub n's is Riemann-Stieltjes integral. And that's true for k equaling 1, 2, 3 forever. Okay. By a previous theorem, since we have the f sub k's are converging uniformly, and each one of them is Riemann-Stieltjes integral, the one we just did. So by the previous theorem, that's why it's corollary of it. F is an element of Riemann-Stieltjes integral functions on a to b, and the integral from a to b of f d alpha equal to the limit as k goes to infinity of the integral from a to b of the sum as n runs from 1 to k of f sub n's d alpha. That's by the previous theorem. And that's equal to, by having a finite sum inside the integral, we can take that out. So here this should be n running from 1 to k of integral from a to b of f sub n d alpha. And that's equal to the sum as n runs from 1 to infinity of a to b of f sub n d alpha. And that's what we were trying to prove. Okay. In our work here in chapter 7, we had considered an example. And let me write down what example I'm talking about. We previously considered the sequence of functions f sub n of x, where f sub n of x is equal to sine of nx over the square root of n. Where x is an element of the real numbers, and we have n equaling 1, 2, 3 forever. And we noted that the f sub n's converge pointwise to f equaling 0, identically 0, function on R, but the derivative of f sub n of x was equal to the square root of n times cosine of nx, and the derivative of f was equal to 0. So that the derivative functions do not converge pointwise. To f prime, okay? So that's something we'd already noted. Okay, it turns out that these f sub n's converge uniformly to f of x, or to f equal to 0. But the derivatives do not converge uniformly to f prime. Okay. So, kind of a summary, what we had was uniform convergence of f sub n's preserved continuity and integration properties we saw that, but with this example we realize does not preserve convergence for differentiation. Okay, so what would it take to do some kind of differentiation, preservation? What more than uniform convergence? And that leads to our next theorem. There. Says suppose F sub n is a sequence of functions that are differentiable on A to B, and such that the sequence F sub n of one particular value, x sub naught, converges for some point x sub naught on A to B, if the sequence of derivative functions converge uniformly on A to B, then what we have is that F converges uniformly. I shouldn't say F, the F sub n's, the sequence F sub n's converge uniformly on A to B. To a function F, and the derivative of F is equal to the limit as n goes to infinity of the derivative, the derivative of F sub n's of x, where x is an element of from A to B. Okay, this proof is a little bit long. I'm going to assume what we have here. We're going to let F sub n be a sequence of differentiable functions on A to B, such that F sub n of x sub naught converges for some x sub naught in A to B. We're going to let the sequence of derivative functions of f sub n converge uniformly on A to B to a function. We want to show that the sequence of f sub n's converge uniformly on A to B to a function f, and whatever that function that it's converted to, which we're calling f, And the derivatives function for each x is equal to this limit as n goes to infinity. I'm sorry. That f prime of x is equal to the limit as n goes to infinity of f sub n prime of x. Okay. We start off by letting epsilon be greater than 0 be given. Since the f sub n of x sub naught converges, this is just a sequence of numbers, okay? Then f sub n of x sub naught is Cauchy. So there exists an integer, we'll call it n sub 1, such that for all n and m bigger than or equal to this big N sub 1, the absolute value, or norm, for complex base functions, of f sub n of x sub naught minus f sub n f sub m of x sub naught will be less than epsilon over 2. Since the sequence of the derivatives of the f sub n's converge uniformly, then there exists an integer n sub 2 such that for all n and m bigger than or equal to this big N sub 2, I should say, then the norm of the nth derivative evaluated at t minus the derivative of the nth function evaluated at t will be less than epsilon over 2 times b minus a. Okay, and this is true for all t element of a to b. And this is a true result because of the convergence uniformly working with the Cauchy criterion for uniform convergence. We're going to let n equal to the maximum of n sub 1 and n sub 2. Thus, for all n and m bigger than or equal to this big N, we have two things. This norm of the f sub n evaluated x sub naught minus f sub m evaluated x sub naught will be less than epsilon over 2, which we said before, and the norms involving the derivatives, f sub n prime of t minus f sub m prime of t, will be less than this epsilon over 2 times b minus a. And that's true for all t element of a to b. Now, since f sub n prime exists on A to B, then f sub n is continuous on A to B. And this is true even if the f sub n is a complex value function. Okay. So that means that f sub n minus f sub m, we look at that combination of functions, is continuous. Okay, on A to B. And the derivative also exists on the open interval. So it's a closed interval, really. So we'll concentrate on that open interval for a second. We had this, the mean value type theorem, and that was for vector value functions, and so if f sub n's are complex, we can think of them as vector value functions. On f sub n minus f sub m, giving us, okay, here's what it gives us, f sub n of x minus f sub m of x minus the quantity f sub n of t minus f sub m of t, that norm, is less than or equal to the norm of t minus x times the norm of f prime sub n of x sub 1 minus f sub m prime of x sub 1. And that's true for some x sub 1 between t and x. And this quantity then will be less than, this norm here, this difference here, will be less than t minus x times, here, this is going to be the epsilon over 2 times b minus a, and which is definitely going to be less than epsilon over 2, and that is true for any x, t, n, a to b, and for all n and m bigger than or equal to our big N. Okay, so that we get this inequality of the norms of the difference of the derivatives. Now note, f sub n of x minus f sub m of x is equal to, well, let me write down here, the norm of f sub n of x minus f sub n of x, f sub m of x minus f sub n of x naught plus f sub m of x naught plus f sub n of x naught minus f sub m of x naught, which would be split up with the triangle inequality, be the norm of f sub n of x minus f sub m of x minus f sub n of x sub naught plus f sub m of x sub naught plus the norm of the f sub n of x sub naught minus f sub m of x sub naught. Now, this part here is going to be less than or equal to epsilon over 2 plus this guy is less than or equal to epsilon over 2. And that's equal to epsilon. And that's true for all n and m bigger than or equal to this big N. And for all x element of A to B. Let me write this down here. This part being less than epsilon over 2, we had just shown previously, so that's our previous work. So, by the Cauchy criterion for uniform convergence, the f sub n's do converge uniformly on A to B. Now, we'll let f of x be equal to the limit as n goes to infinity of f sub n of x. So f is the function that the f sub n's converge to. Now what we do is we fix x element of A to B and define the phi sub n of t to be equal to f of n of t minus f sub n of x all over t minus x, and phi of t to be equal to f of t minus f of x all over t minus x, both of which will be part of derivatives involving computing derivatives. And we're making this definition for all t n A to B with, of course, t being different from x. Now, we note that the limit as t goes to x of phi sub n of t is equal to f sub n prime of x. Okay. Now, since the norm of f sub n of x minus f sub m of x minus f sub n of t plus f sub m of t is less than or equal to t minus x times epsilon over 2 times b minus a. This is true for all n and m bigger than that big N that we had earlier. We have that the norm of f sub n of x minus f sub m of x minus f sub n of t plus f sub n of t over the t minus x is less than or equal to epsilon over 2 times b minus a. That implies that the norm of f sub n of t minus f sub m of t will be less than epsilon over 2 times b minus a. And that's true for all n and m bigger than or equal to this big N. Now look, this guy is really arbitrary. You know, we picked epsilon. I can make this one to be less than any epsilon I want. That's what this is saying. And so, by the Cauchy criterion for uniform convergence, the phis of n's converge uniformly on A to B, okay, except when t is equal to x. Okay. Now, since the f sub n's converge to f uniformly, we have the limit as n goes to infinity of phi sub n of t equal to, using the definition of phi sub n of t, it's the limit as n goes to infinity of f sub n of t minus f sub n of x all over t minus x, which equals to, well, as n goes to infinity, the top will be f of t minus f of x all over t minus x, which equals to phi of t. And so what we have is that the phi sub n's converge uniformly to phi for all t element of A to B, with t being different from x. So it's almost all of them except when t is x. We're almost done. Note, x is a limit point. The interval from a to b minus, take away just the x. And we have, it's already been stated, the limit as t goes to x of phi sub n of t equal to the f sub n's derivative evaluated x and the sequence of the f sub n's converge uniformly to phi on a to b. On a to b, I'm sorry, almost. On, let's write it down here. A to b minus the singleton x. Then by a previous theorem, it's the theorem that ended lecture 26, I believe. The limit as t goes to x of phi of t is equal to the limit as n goes to infinity of f prime sub n of x. And so that gives us the result we want. That is that this quantity is nothing more than f prime of x is equal to the limit as n goes to infinity of the derivatives of x. Okay, that's what we wanted to show. So that concludes the lecture for today. Thank you very much.